What's up, guys? It's Ferdinand Nandi here of Class D Power Amplifier Project. This is the TPA3255, the Module B that I'm testing it right now. And in this video, I'm going to show you how I do the test parametrically. And guys, I began to dislike this solution. I mean, not the TI chipset solution, but probably specific to this board, which is I don't like it so much. And the reason why? Well, you have to stick around to this video until the end and you will discover with me why I don't like it. Alright, things put up ready. LED is on. Without zero input signal, let's power it on. This is a 31 volt DC power input. This is the residual noise. The clock frequency is actually at about 454 kilohertz. We have this because of the clock frequency, which is about 269 millivolt. This is from the oscilloscope capture from the PC. And what I get from the O1 oscilloscope is like 235 millivolt at about, let's just say 453 kilohertz. That's the clock frequency of this Class D amplifier. Once again, the TPA3255. The input voltage is about 31 volt DC. And currently, the temperature at the heatsink right now is at 33 degrees centigrade. That's the one in there. And you can see how terrible it is. But don't worry about that, guys. You can't hear that one unless otherwise you are a superhuman ear. And that's the reason why I got the O1 oscilloscope, the standard bench test oscilloscope, to actually see the real waveform that we can see from or we can get from the TPA3255, not just to follow this PC-based oscilloscope. And exactly they are performing the same. They're giving the same information, how scary it is. Of course, you cannot find this in Class A power amplifier or Class B power amplifier. I need 2.8 volts voltage swing of the resistive load. This is the capture of the PC, and again I'm comparing that one with the capture from the standard oscilloscope. It reads here 2.6 volt RMS at 1 kilohertz. I may need to increase the amplitude to something like exactly 3 volts is okay, 2.9 is okay, and that's it. And what's the reading in here? There seems to be 1 volt difference. But anyway, as long as the measurement is standard, and that's okay for me. Now I'm going to see the distortion at this level at a rising temperature of 41 degrees centigrade at the surface of the heatsink. We got the total harmonic distortion plus noise is 0.02% for the left channel. And for the right channel, that is 0.019%, which is pretty good actually. That's something that quite interesting to understand about the distortion, wherein several hobbyists may not be able to understand that because of the lack of equipment. So I wanted to make the one showing it. Now, don't worry about this, guys. I know that there is a clock frequency going on there, but it is also, I'd like to explain about that one, which is also affected by the resolution of the DAC, which is, you can see in here, 8-bit and 16-bit, and the maximum that I can able to get it from here is the sampling is about 16-bit. If there will be like 32-bit, that would be better. So you understand what I'm saying is that this is at 8-bit right now. So the DAQ sampling or the DAC sampling is much lesser, so you can see the real stuff in here. That's pretty scary, right? And when I change that one into 16-bit, that's the 16-bit, and you can see what's going to happen. So it's a finest, nicer, and that's explain a little bit of the measurement limitation, which is why I'm using the standard oscilloscope just not to be fooled out of it. By the way, guys, how do I look right now with this kind of dress? I mean, the reason why I'm wearing this kind of dress right now while I'm doing this hobby electrical performance test is that I get a new job and I was required to wear a little bit nicer clothes, not like those sports clothes. And this is a good training ground, my practice while I'm doing the electrical performance with the Class D power amplifier from Texas Instrument, which is the same thing that I'm going to do in the new job. This is required for me to do the advanced test. I forget to mention about the offset voltage, which is on the right channel is about minus 4.3 volt millivolt, and on the left channel there is a plus 20.4 millivolt. That seems to be a good performance, which is I love it, I guess. At this time, I don't see anything that makes me dislike it. I like the form factor actually. Let's go back into the quantum oscillum captures. You can see also in here the signal to noise, which is being measured about let's say 75 dB for the left and the right channel. There is one thing that I'd like you to know, that the oscilloscope right now is not using the AC power. It's basically operated using a battery. So this oscilloscope right now is not a ground reference, just like these two equipment right now, which is not ground reference. And I believe that the PC is also not ground reference. The main reason why I brought out again about the grounding is that the speakers in here, these speaker terminals in here, they are in a BTL mode called bridge tide load, which is none of these are referred to the ground. And if you're going to make use of the grounded equipment, then this amplifier may not work. I don't have the differential probe right now. That is why I need to do something about the grounding system. And that is also the reason why I'm not using the AWG, that is the arbitrary waveform generator from this multi-instrument, because this BNC here, it is a ground reference. Rather, I'm using the external AF generator, just easy for me to hook it up. But this equipment is basically a ground reference. And that is also the reason why I don't use the quant oscillum. This is like separated from the ground, but it is easy for me to just turn the knob in here when I'm doing the measurement, rather than doing the kind of adjustment on the software like the generators in here. It's a little bit not convenient just to do the click, 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 rotating the knob as in the standard audio generator is easier for me right now. Well, how do I look? Let me know on the comment below, and maybe you can suggest something, a kind of color for dress, daily dress that I can use it going to the company, because I'm not used to this kind of dress actually. Alright, let me move to the most interesting part, which is I'm going to crank the volume right now to its maximum, and I try to understand about the artifacts. I know that there should be like a necktie in here. I'm not so sure where can I get the necktie right now. It must be uncomfortable, and that's the reason why I'm doing the training ground right now with my hobby. I hope I'm doing well with this kind of clothes. I don't know if it is the right color, the right combination. I don't have my watch right now. I don't have this watch right now because doing the electrical performances, actually you are forbidden to wear the watch except for the ground strap in the real job in the company, and also for the rings because it might interfere with your test and with the concept of ESD policy. Yes, that's the same thing I'm doing in here. No watch, no earrings. I'm not married right now. I'm free, I'm free, I'm free. And I'm going to increase the one, increasing. All right, you can see the top of the waveform. Maybe I just need to show the right channel, the left channel. The yellow one is the left channel. And you can see it is being deformed. Maybe you can see that one later into the oscilloscope, which is the reason why I need to. Now, don't be too scary about the one. If you take a look at in here, the capture of the PC-based oscilloscope, you can see in here is a little bit distorted, which is a little bit scary. But when you take a look at the distortion, that's still like 0.0086. And if you're gonna compare that one to the capture of the oscilloscope, it's much cleaner in here. There is no distortion. That is the reason really why I had this oscilloscope, to view the actual signal that is happening lively, not in this oscilloscope capture in here, which is pretty showing there seems to be a problem on the top. When I'm going to let me put the tripod. There it goes. Let me put. Oh, sorry. Let me put the tripod. Okay, much better right now. So you can see in here, this is nice at the top, but when you increase it, it's a little bit distorted. It's not following it. Again, this is a problem on the measuring equipment due to the DAC, which probably cannot really follow it. So increasing further, you see, it's becoming much better, but this one is the worst one. So increasing further, now there you are. It seems going to the distorted again. Increasing further, now is the artifacts. No, I need to turn off the QA401 because I cannot exceed the 20 volt. The 20 volt RMS input. So I have to. Oops, what's going on? So I have to disconnect the one in here, remove it, hang it, and now I just have to concentrate only on the waveform right now. And you can see the artifacts right now from the top. It seems to be quite obvious, but let's see from the oscilloscope. Yes, that one is also obvious. We can see the artifacts over there right now. And we have the input power right now. Sounds like about 100 watt. Oh my god, I'm just can smell something at 50 degrees right now. Anyway, I know that the TI chipset comes with the temperature protection, like also a thermal fallback, sounds like that. So we are in the testing and no worry about that. So increasing further, the artifacts at the tops and bottoms is definitely ugly already. I'm not so sure if this is 1% or that is a 10%. Unfortunately, there is really a limitation of the QA41, and it says there that I can't input more than 20 volt RMS. Otherwise, it's not going to, probably it will going to damage it. But we can see from here and confirm that the artifacts at the tops and bottoms is only happening. This is the real one, artifacts in here. And when that happened, we got also the artifacts from the oscilloscope, which is the real stuff, are about this power, about 100 watt input power. And what's gonna be the power at that time? There is a 21 volt RMS. Let's see. Before that, I'm going to show the A and B, that's mean the left channel and the right channel. And it does happen for the left and the right channel. Let me put that one into, this is 50 volt already. How I'm going to separate that one? Yes, it's absolutely happening also for the right channel, which is the pink one. Just wanted to separate only the left and the right channel. Let's just do some kind of experiment here. What I'm trying to say is that I'm going to make use of the QA401, and then let's see at the 20 volt RMS input. No, that's 20 volt RMS output, the voltage swing at the 8 ohm speaker load. And let's see what's the distortion at the 20 volt RMS output. Let's see, we're gonna monitor that one not to exceed that's 50 volt. Right, let me put that one into 50 volt. Okay, there you go, there you go. All right, let's just to be fair, that's 19 volt RMS of the output, and we still see a pretty good distortion in here, about zero point 0.1 or zero point 0.2 on the right channel. Why is it so? Why the right channel is higher in distortion? That's the evidence. We can see that one. Let's see that closer. Yeah, let me position that one. So I can choose, this is A. Yeah, there is a little bit of data, and when you superimpose that one with the B, there you go. It's each bigger. Actually, you can see the difference in here. Probably I can make that one into larger one, like 20. All right. Now you can see the separation of the left and the right channel signals, and that's really explain the way I look at it right now. Why we have a higher distortion at the right channel. The right channel is the pink one, and the yellow one is the left channel. Put that one again to superimpose. There you go. I'm not exceeding the 20 volt RMS right now at the input of this QA401. Let me verify that one. Really? That is just about 17 volt RMS. Well, let's put that one into something like 1920. And what do we get in here? What I'm trying to say is that this is a 20 volt RMS output at the 8 ohm resistive load, and the oscilloscope says that is about 19.2. I can increase that one to 20. Pretty cool already. And this is what we got in here. We got 21.1 volt RMS, and we got now the distortion increases to 0.1, and the right channel is thus increased to 0.4. So this is how it looks like right now. Really can see the difference of the two signals, which implies on the distortion. So what's the maximum voltage that I can assume to be at 10%? I just had to estimate it because I cannot make use of the distortion meter right now. So assuming that this is 5% and probably this 10%, so about 23 volt RMS. 23 volt RMS, when I computed that, that will be like, let's see, multiplied by itself, that's the voltage swing, divided that by, this is the left channel, and this is divided by 8 ohms, that is 66 watt, and multiply that by 2, so I can produce 132 watts. That's the average power, or sometimes they call it the RMS power. That's the stereo power that I can squeeze from the TPA3255 from the input power of 31 volt DC. That's a single supply. Just a single supply. I need to clarify that one because some of the amplifier that I'm working, they comes with a split power supply with a plus and minus. This one is only a single supply. That's it, and the temperature right now is at 57, like 57 degrees centigrade. And I just keep continue with some power in here, just to keep going with the test. So this is a challenge, guys, that I have only 31 volt SMPS power supply right now. That one is standard in my best right now. So I reached out to my maker friends here in the Bandung province, specific to Shenzhen or Dongban, that if they can able to lend me a kind of SMPS power supply that is above say 50 volts, and the power capability should be like 800 watts or even up to 1 kilowatt, and the response from the maker community here in Shenzhen, I can mention about the troublemaker headed by and manned by Hank, and I guess that I have a lead that I can borrow one Swiss wood power supply from one of the maker. So I'm back, guys, I'm back, and I got the Swiss mode power supply already. New muzzle. 2, 1. There goes. I'm so ready. It's no problem, no problem. There is no any grounding in here. And you know why I'm doing like this, right? Instead we are doing like that. So that when there is a shock, it will go like this. So finally, I finished all the electrical performance of this TPA3255 right now. When I'm going to use the 48 volts 800 watt SMPS power supply, I can get like about 136 watt of pure power. That is the average power, or sometimes they call it the RMS power, which is 136 multiplied by 2, like 272 watt stereo power. That what I can squeeze from the 8 ohms resistive load. So what do you think, guys, about the power capability of the TPA3255 at the 8 ohms load? That is a 1 kilohertz signal, maybe 10% distortion, 136 watt per channel. Well, if you ask me personally, that's really awesome. That's pretty cool in reference or in compare to my favorite chipset, the TDA8920, the TDA8950, or even the TDA8954, which is sad to say that this chipset, they're already EOL, end of life, and that's the reason why I'm venturing right now into the TI chipset, the TPA325X series. I would say from the electrical performance that the TPA325X series, especially the TPA3255, is an excellent chipset. It's a very good chipset, except one thing that I don't like so much, which is I really don't like it. Frankly speaking, personally speaking, honestly speaking, I don't like it. And that is it protect itself. It's like it really protect itself. It's like it shut down, and there is no way you can revive that except with a cold reset, which means to say that you need to power off. Power off the power supply and then power it on again. That's something that I don't like personally. I say again, honestly speaking, I don't like that. You're probably asking why I don't like that. Because I don't like it because I have seen other chipset like the NXP or the Philips chipset. I mentioned to you about my favorite chipset like the TDA series, TDA8920. They don't behave like that. There is like a better algorithm where you can shut down itself, and then when you are already okay, then you check again, and then you can revive yourself, like self resetting. But this chipset, what I observed so far is that it won't revive or reset itself when there is a kind of fault, like the temperature fault, when the heatsink can no longer dissipate that a lot of power that is generating from the chipset, then it shuts down itself like a temperature protection, then it won't revive itself. That is why I'd say that I don't like it, because I have a reference chipset from NXP that performs better. It could have been, there's another way that it could revive itself, that would be much better, to be more of a robust chipset than what is the performance right now. But I think I need to check the datasheet if this is really the performance. I did not completely read the datasheet, and probably that is the one that I'm missing right now. What is the finale? I'm happy to inform you that while I'm making the electrical performance, I'm also making the report. I try to do that one in a Word file without editing, just Word file, and you can actually, guys, download that from my personal website. That's called onediywshare.com. I hope that it's still alive and still can able to pay that through the years. I link down where you can download the report about the TPA3255, and then you can find yourself, criticize it, put comment on it. Probably you can improve the description. You can actually put more words, or maybe correct my English grammatical way of writing that. I really made it rush actually while doing the electrical performance, and that is the reason why I am sharing it in a live Word file, so you can modify it. That's what I can do and share right now with the experience on TPA3255. Basically, the TPA325X series. Once again, the three brothers, the TPA3250, the small brothers, the TPA3251, the middle brother, and finally the big brother at my back right now, the TPA3255, the big brothers. I think this is already a pretty long video, something that I have done actually this in the last 3 days in making this video and electrical test performance, waiting for the switchboard power supply. It's 3 days compressed to something like 20-25 minutes video. But it's pretty cool, it's a lot of fun, and it's a lot of learning that I acquire in lively performing the electrical test. Alright guys, it's Ferdinand and once again, and thank you for watching my class test series of Power Amplifier Adventure. And if you like my videos, you might consider to subscribe by clicking the subscribe button. You might like to share these videos to our audio hobbyists, and of course you can write some comment below if you feel like to write something, or if this video is not so good to you, your own perspective, you might like to put this thumbs down so that I can know what should I do to improve my video editing, myself DIY filming, being a content creator here at YouTube. Those are the kinds of informations that it will give back to me as a content creator for me to improve my next videos. This is really it, guys. This is really it. Bye for now, and see you in the next video.